Hello everyone, Aaron here and welcome back to Leetcode. Today we're doing the minimum time to collect all apples in a tree problem. Given an undirected tree consisting of n vertices numbered from 0 to n-1, which has some apples in their vertices, you spend 1 second to walk over one edge of the tree. Return the minimum time in seconds you have to spend to collect all apples in the tree, starting at vertex 0 and coming back to this vertex. Okay, so we start at the, I assume is the top, and have to make our way back. The edges of the undirected tree are given in the array edges, where edges I is AI, BI, means that an edge connecting the vertices AI and BI. Additionally, there is a Boolean array hasApple, where hasApple I is true. It means that the vertex I has an apple, otherwise it does not have any apple. I assume that's what these red ones are. False. Yeah, so 2 here has an apple, so it's colored in red. 4 and 5 both have a true let me try that again. Are both marked as having an apple, true, so they're colored in red here. So the edge is given here, layout like this. And to collect all the apples, we need to go 1, 2, 3, 4, 5, 6, 7, 8 steps. Another way of thinking about that is we collected 4 edges to connect all of the apples, and 0. Here only 5 and 2 have apples, so we need 1, 2, 3 edges, so the answer is going to be 6. And here there are no apples, so we are done. Right. So just trying to think how we want to do this. What are the constraints? N can be very large, so these can be huge trees. The number of edges is n-1. So these things are connected. There's never going to be missing edges or extra edges in any way. Every edge has a start and an end. AI is less than BI. So we're always given these things in numerical order. So we're given 1, 5, never 5, 1. From I is less than 2i. What's from and to? I don't know what from I and to I are. I think that just means that a child node has a greater value than its parent node, and we are given n nodes about where the apples live. Okay, there's a lot of setup for this one, but I think all we need to actually do is start at the apples, work our way back to vertex 0, which they must eventually reach, and double the number of edges we've managed to collect. I think that's the algorithm. So, used edges, let's make that a set, just so we know. And we want to return len used edges times 2. Right. For I has apple and has enumerate has apple. Let's do used pass for now. I'm not quite sure. So, in fact, I know something about this. if has apple, we want to do some sort of to root from the I with the edges. In fact, I think this is what we actually want to do here. So my thinking here is that if I say, well, this one's an apple, I want to walk up to... In fact, I can do slightly better than that, can't I? It's self.used vertices is also a set. So what I want to do is I want to say, well, if I start at 4, I need to walk up to 1 and then up to 0. So I'm going to use these two edges. Then if I start at 5, I'm going to walk up to 1 and then I can walk up to 0. Well, that's what my original plan was. But I think if I only really need to walk to 1. Once I've walked to 1, I can stop. Every other edge above that is going to be dealt with already. And the 2, that walks up to the 0. So, walk to visited vertex. The current is going to be the start, while occur not in self.used vertices. Self.used vertices.add current. And now what I want to do is, what is it I want to do? I might change how this is set up. For convenience, but basically the idea is that for edge in edges, for from to in edges, if 2 is the current thing, we are going to follow it back up, and we're going to do self.used edges.add from 2. So if we're starting at 4, we're going to add 4 to our used vertices. And then we're going to find the edge that walks from 4 up to its parent. And in fact, that must be unique. So we don't actually need to do a search here. Yeah. If cur in self.edges from is equal to self.edges current. And then we want to change the order of these. I'm not being very articulate about this. So let's not call this from, let's call this parent. So what I'm going to do is I'm going to change what edges looks like. This is going to be in fact, let's call it parents, just because it'll be more obvious what's going on. So find this thing's parent, and then, well, if it has a parent, 0 doesn't have a parent, so we just need to do this little check here. But grab its parent, add the edge parent to current, and then say we're now at the parent. So we were here, we found the parent is this, so we've marked this edge, and we've stepped up. Excellent. I think we can even go better here. I don't actually care what their used edges are. I just care how many I've used. Anyway, so now this needs to change. This is a dictionary. There's going to be to mapping to from. No, in fact, we'll do it from the child, mapping to the parent, for parent child in edges. Except this isn't a tuple. Oops. This is a nested list, which is a wildly inappropriate decision in Python. So we set up this parents dictionary so that we have a child to parent relationship. So 4 maps to 1, 5 maps to 1, 1 maps to 0, 2 maps to 0, 3 maps to 2, 6 maps to 2. The reason we can do this without anything funky is that effectively this is the definition of a tree, that each node has exactly one parent. You're not going to also have something that branches off up here with this 1 going to a -2 or something over here. We're going to count the edges. We're going to remember which vertices we've seen. Then for each apple, we're going to work out how to walk back up towards 0 as far as we need to get on a track we've already seen before. So to do that walk, we're going to say, well, I'm starting here. While I'm off the beaten track, I need to mark this as on the beaten track and step up to the parent using 1 more edge. This counts the edges, 1, 2, 3, 4, so that's 8 steps to actually traverse it, which is straightforward enough. That passes all the test cases, which is nice. So let's submit it and see what happens. Wrong answer. Oh no. 0, 2, 0, 3, 1, 2. That's not a valid tree. Oh, it is a valid tree, but it's not a rooted tree. Oh god, that makes this problem significantly harder. What do I want to do about that? So this tree, 0 to 2, 0 to 3, but there's also a 1 to 2. It looks like a backwards N. The 1 is... The 1 has no parent. It's undirected. Bugger. The problem is, it's undirected, so you can walk from 1 to 2, then 2 to 0, and that's the 2 edges you need. Ugh. So we can still do it. but it does become significantly more difficult. We're going to walk to 0. We're going to revert this to being a set of used edges. Just for convenience, this is no longer going to be parents, it's going to be neighbors. We'll make that a dictionary to begin with. For A, B in edges, if A in self.neighbor. Hang on. Let's do this with a default dict. Import collections.default dict of a list. Self.neighbors a.append b, self.neighbors b.append a. Walk to 0. So here what we need to do is effectively something like a breadth first search. So visited is going to be a set. The queue is going to be a collections deck containing the start to begin with. In fact, we'll make it a tuple containing just the start. If you've not seen this before, this is all sort of how I usually set up these kind of graph searches. So I'm maintaining an entire path, while queue path is queue.pop left. And then it is if path -1 is equal to 0, found a path. I will come back to that. Then it is visited dot add path -1 for next in self.neighbors of path -1. Let's call this just n because next is a reserved word. What I want to do is queue.append path plus n. If path -1 in visited continue, I don't want to go back to the same place I've seen many times before. I think that is a valid breadth first search, which I have now coded up incredibly quickly. Apologies for rushing through that. So the general idea is you maintain a queue, and the queue is going to contain all the paths we're currently working on. So I'm going to take the next path that I need to deal with. If it's reached the goal, amazing. Stop, process it. We'll do that in a second. Otherwise, if we've already been where we've got to already, don't bother. Mark this as a place we've already been, and then visit all of the neighbors. Where can we get to from here? So it's now just this processing thing. For I in range len path -1 self.used edges dot add path I plus 1. That needs to be wrapped in brackets. Now the trick here is we're going all the way back to 0. We don't really need to do that. I'm saying walk to 0, but it is still more of a walk to where we've been. Or we can optimize it in that same way. Walk to known vertices. So walk to known vertices. And then here, if path -1 in self.use vertices, this is when we can stop. So here what we want to do is then self.used vertices.add path I. So here, once we've actually finished our breadth first search, we're going to record all the edges we ended up using and mark all of the places we visited as vertices we'd visited. Generally, we can't do that as we go because this visited set is different to this visited set. This set is just for our local search. Some of the paths we take won't actually be the right path, whereas over here these are ones that were definitely on the right path, so we can mark them as good. So can I use this as a test case with n equals 4? These edges and these has apples. Oops, there's no underscore in default dict. Collections .deck. Silly typos. Oh, many silly typos. If you can't tell, I don't use Python day to day, so I'm not entirely up to speed on its standard library. I will be soon using it day to day, but not at the moment. Not to mention, it doesn't help that the collections module has some of the least consistently named parts in the whole system. Oh. Used vertices needs to start with a 0 in it. Just so I know that I can reach the end. There we go. That seems to work for all of them. Let's submit it again. Looks promising. There we go. Excellent. Our runtime was actually excellent, and so was our memory was meh. We probably didn't need to be storing all the edges that we actually used. We probably could have gone back to a counting approach. But anyway, it is what it is. It worked. Excuse me. I wasn't expecting to have to do a breadth first search because generally trees are simple enough. You don't need to do that kind of work. But it was just the shape of the trees was very slightly inconvenient for what I needed to do. They were undirected and unrooted. So anyway, that was quite a neat problem, actually. A bit of a challenge over some of the ones we've done recently. This is a genuine medium, I think, and a fun challenge. Anyway, that is going to be it from me. Do remember to like, comment, subscribe, all of that good stuff. Did you manage to avoid using your breadth first or depth first search, or is that just the way you have to do this problem? Anyway, I will see you next time. Oh, programming note. I may not be able to upload tomorrow. I will do my best, but it's going to be a busy day for me. So maybe no video tomorrow. Hopefully there will be. Anyway, bye for now.